Antiderivative. You guys know what it means, but explain it to those that might not as well. What is an antiderivative of a function? The original given the derivative. I like that. It's the original given the derivative. So what kind of function is going to have a derivative of 2x? X squared. Choking on my protein bar. But not just x squared. Yeah. The general form will be a quadratic, will be an x squared. Could not have a linear portion, but it could have a constant. Could have any constant, because the derivative of any constant is 0. Now, why is this guy a little bit harder? P.S. Original functions, we name f of x. Antiderivatives, we name capital F, just to be able to keep them straight. And I really, really, really think this is an important part of an antiderivative. Why is that guy harder? Number 2. Coefficient and the original power.
So 2x to the 5 halves.
Okay. So Justin went really fast because we did a lot of practice last year and his brain retains really well. So when he says 2x to the 5 halves, he's already thought through a lot of different things. Let's think through what he's had to think through. Why did I expect a lot of you guys, or all of you guys, to be able to go from 2x to x squared? Because you've seen this derivative over and over and over and over and over again. 2x is a derivative. Where does it always come from? X squared. Not too bad. So let's think through what happened. Why did the power have to go up 1? Because derivatives because the general power rule for integration, which we'll talk about later, says always take the current power when you're finding antiderivatives and add 1. So we can do that to this power. But when you add 1, remember, whatever this new power is has to come down. And when it comes down, well, this one we wanted the 2, so it was fine. We didn't put any coefficient. We didn't need it. The 2 would come down and form our original function. But this one, do I want 5 halves to come down? I want the 5 to come down, but I would need the half to go away. So what needs to be waiting for it? A 2. Or you can also think of the original coefficient, which is 5, if this makes it any better. The original coefficient, which is 5, needs to be multiplied by the reciprocal of that power, which we talked about last year, x to the n plus 1 all over n plus 1 as one way of doing the power rule. So I need to add 1 to get the power back to where it was before it subtracted 1. I need to divide by or multiply by the reciprocal of that, because that's the only way that my powers will match when I take the derivative. So our final answer is, as Justin says, 2x to the 5 halves plus c. Why this showed up in this section is at the very, very bottom of the notes. That MBT was actually an integral part. I probably shouldn't say that. Was an important part as to why the plus c is necessary and even allowed. I'm not going to go tons into depth on that. It was interesting. That's why it got brought up in this section. This is where our book chooses to say, hey, guess what? There's this thing called an antiderivative. Guess what? We need, for the entire family of antiderivatives, a plus c. And it decides to talk about why MBT was instrumental in that. But I don't think that's super important for our full understanding. We have a lot of other things to do today. So let's get to the homework, because I know you guys have some questions. But first, I want to show you a peek into what we need to do. Oh, hey, there's rolls. We mentioned it yesterday. I just didn't show it to you yesterday. There is a forever card from AB. I need to update the forever cards. I'm sorry, Sally. I haven't gotten the new ones up. So I need to update those. Actually, I think I posted all the forever cards from last year in your notes, right, guys? Okay, so I think they're already all there. But we're definitely up to Rolle's theorem now. But as we said yesterday, Ariane, you said it. What was the most important characteristic of Rolle's beyond MBT? But technically, if f of a does equal f of b, couldn't we still say f prime of c is equal to f of b minus f of a? Because what happens if they're the same? I get 0 over b minus a. So I end up at the exact same conclusion, which is why some people just don't even really talk about roles anymore. Not that it's bad, just they would rather their kids know MVT and not necessarily stress about roles as well. You can still use both technically, though, on the AP, but roles is only applicable if f of a equals f of b and if you are talking about a horizontal tangent. With that, sorry. Section 5.3 is saying, let's talk about graphs of who knows who, of f prime, of f double prime. Let's talk about graphs and all the different ways we can analyze. So there's a lot in there, so let's go ahead and go over homework, okay? I heard there was some nasty stuff going on, specifically to do with extrema. Was that what we were talking about at the beginning of class? What page was homework on? Yeah. Zoom, zoom. Zoom, zoom, zoom. All right, I have homework up and ready, but let's go ahead and check our answers first. So number 10. Boop. 10a. Don't go to decimals, guys. You know better than that. 1 over root 2x minus 1 over root 2 or square root of 2 over 2. Secant line, we just had to go ahead and find our x1, y1, which means we had to plug into the function our x's to get our y's. And then it was a simple change in y's over change in x's. Then we could plug it into our tangent line at the point of tangency. Who was the original function? So if you plug in 1, you get 0, right? Did they give you a sketch or a graph? They had to give you something. Is this the wrong homework? Wait, this is the right homework, right? Yeah. Oh, number 10. Got it. Sorry. It says tangent line to AB. Wait. In the interval that is.
First, you have to find the AB line.
Oh. They're saying the secant line AB, that's just y minus y1 equals m times x minus x1. So we just went ahead and, or you could have gone ahead and just done y2 minus y1 over x2 minus x1. You didn't have to choose 1, 0. Both of these points are on the line. You could have chosen the other guy, just most people wouldn't want to choose that if they didn't have to. So technically, it could be, this could be different. It could be x minus 3 plus square root of 2, but that would have remained the same after you simplified. Should have anyway. And then letter B says, okay, that's the secant line. Where would the tangent line be parallel? Just think parallel. Slope of the tangent line, where is it equal to the slope of the secant line? So you would take the derivative of f. You would set it equal to the 1 over root 2 or square root of 2 over 2, whatever you did up here, and then solve for c. And you should have ended up with 3 halves.
Yeah, I got that.
Cool.
And then I didn't know if it was.
But they wanted the point. So then the point, yeah, go plug in to get the y value. And then you can actually make the tangent line by stealing the slope and then using the point. And they just plugged into point slope. So you find the c, then you find the f of c for the y1. And then plug in the m.
Why are they doing 1 over square root 2 instead of square root 2?
Long story short, it's simpler to work with. In Algebra 2 or Pre-Cal, we would have rationalized it to be square root of 2 over 2, but it's a lot simpler to do like the reciprocal if you were doing perpendicular. It's just a simpler form, even though it's less finished, I suppose. Is that okay? Number 12. This one you're having to justify for, right? Give you the average rate, or did you have to find that? It was 2 seconds. Okay. Well, let me give you guys a second. Let me freeze the screen. Let me sign back in, because I know we have some questions. Sorry, guys. Bummer. Yeah, so A was none. Strictly decreasing, I mean, that's another way of saying letter B, right? Oh, okay, so it's not increasing, so C, it's strictly decreasing. Number 30 and number 40, number 30 and number 34 were just antiderivatives. 34 could have been a lot messier with a chain rule, but you didn't really need U sub, right? And I think that was the last even. I gave you guys, oh, sorry, one more. I gave you guys mostly odds, I hope, didn't I? Okay, because I wanted you to be able to check. I gave you some evens, but only on the things I thought you guys would be okay on. So there's number 38. Yeah. Real quick on 38, just for the, well, I guess Eric's not here today, but Sally, for you. When they give you a point, you can plug in the x and plug in the y and solve for c. So that's how they finished that problem. Okay. Maggie, I'm ready. What's odds, kid? Okay.
I mean, I did it, and it was like a simple, like simple question of Sherma, and then I checked the back of the book, and they have these weird numbers. And so I didn't want to do it with graphing, because it didn't say we couldn't do graphing.
Right.
I tried doing it with, like, math.
Without the weird numbers, and it wasn't working?
And I couldn't figure out how they got 8 over 3 as the maximum.
Okay.
And then when I tried to,
Was it one of those things where they were giving you the maximum value, like the y? Could it have been that? Okay. So let's start with the derivative, and let's all double check. So the derivative for, Maggie, what'd you get for f prime of x?
the square root 4 minus x plus x over 3 square root of 4 which simplified into 2 over square root 4 minus x.
What was in the numerator?
Oh, I had 2 and then no 2 at the bottom.
Oh, because it reduced, right? Just 2? I was trying to do it in my head, but this is not the greatest one to do in your head, because then those end up, you get 8 minus 2x. That might have been what happened, because you would have needed to multiply by this top and bottom, and then the square root squared cancels.
I didn't multiply the 2 in.
Yeah, so that'd be 8 minus 2x plus x. I think that'd be 8 plus x. Does anybody match up with that f prime? Uh-oh. No? Second d first, good. Plus first d second. Wait, plus first d second. That should be a negative, right?
Yeah, that's what
Oh, so then that'd be 8 minus 3x. Hey, 8/3. I got it. So I think it was just your common denominator you got messed up on the math. Because then you'll have 8/3. And I bet that's going to fix it all. Yeah. What else do we have on odds or evens if you guys need some more clarification? Yeah. 43b. Thanks, Daniel. 43. As soon as you see free fall, well, they tell you the 1.6. That helps a little bit. How do you guys pronounce that word? Crevasse? No, it's just crevice. What does it mean? Like the valley, like the dipping down, like there's the, it's not cracks. I guess you could think of it as a crack though. It's like a crack in the earth sort of, but it's on the moon, isn't it? Yeah. Anyway. You're dropping a rock into a crevice, and then how fast will it be going? At least that's how I think it, that's how I've always heard it. It might be crevasse. How fast will it be going? That was just a plug and chug. How far below the point of release is the bottom? How far? How do we get to how far given acceleration? Yeah, we need to go from acceleration to position. We need to go 2 derivatives back. So how do we go from acceleration to velocity? we think of the antiderivative. Can you guys imagine like this being your only introduction to motion? I mean, some motion was covered, but not integration. It's crazy how fast they introduce it in this book. Anyway, how do you guys know what C is? Oh, you're down in letter C. Isn't C just the initial velocity when time equals 0? And what's the initial velocity if it's dropped? So if v of 0 equals 0, then pretty quickly I can say, well, 0 is equal to c. So therefore all I have is v equals 1.6 t, which is great for velocity, but I have to go back to position. So I have to go back again. So then you should get pretty quickly 0.8 t squared. Bring down the 2, you'll get 1.6. I don't have a constant, so I'm done. But wait a minute. How far below the point of release is the bottom? I would love to plug in the bottom, except I think the surface of the moon was the beginning, because we made the initial position 0. We could have done a plus c, but I mean we could just have the surface of the moon or wherever you are when you drop it. We could just have that be 0. We need to figure out how far it fell, though. I need to plug in a time. Did you guys find a time? 30 seconds, right? Just before it hits the bottom. It hits the bottom 30 seconds later. So I can just plug in 30. As long as this is being measured in seconds, which I think it is. So then 0.8 times 30 squared. Wouldn't that be 900 times 4/5? Is that right? It should be 180. I don't know. What'd you guys end up getting? 720 meters? Does that make sense, Daniel? Good. Anything else? Evens, odds? Yeah. Not necessarily. Here, tell me what you got and let's see if it matches. Because the one in the back of the book, guys, remember, they had a particular graph probably in mind from the beginning and they made it match, but there are definitely other ways. I think the answer key would probably say something about selected answers vary. Answers vary. It's probably what they say. So Maggie, what'd you do at -1 and 1? Concave up, concave down, linear. Concave down? Okay. Not concave down? Just, oh, the whole thing is concave up? Like that? Oh, like bounce? Like a quartic or something? Sorry. Like that? Let's see. So we have f of -1 and f of 1 both equaling 0. We have f prime being, is this the graph of f prime?
It says the sketch graph of differential function that has given.
Oh, you were sketching f prime instead of f. So you were having, well, I mean, you did it the harder way, I think. So you made zeros of f prime. F prime has to be positive from negative. Oh, you need it to be above, it meaning the f prime to be above if it's positive. So that wouldn't have worked because you would have needed to, you could have gone like this. Because now it's above for that interval, f prime. F prime, man. Protein bar, you're killing me.
Oh, this is the graph of f prime.
Right. Well, I'm going off of what she was doing. And then f prime needs to be negative and positive. There you go. There. Would that have worked? It doesn't say f double prime has to exist, so I can have. So Maggie, that would work for f prime. But what they said about graph was f, because they said the function who has these characteristics, so they're talking about f. So then that's why they should have horizontal tangents here, strictly increasing, decreasing, strictly decreasing. That needs to be increasing. Like that? Will that work? Same horizontal tangent, you have a horizontal tangent. That should have been more that way. And then it's increasing and increasing again, increasing and increasing again. That's what I would have graphed. And it could have been anywhere, because it didn't give me like a point. But I would have done the horizontal tangent, then a horizontal tangent, and then increasing. Is that cool? Okay. Anything else? That one, the directions just messed you up. Okay, so speaking of, actually, Maggie, that was a perfect segue, though, because she was thinking about the graph of the derivative, because in calculus, how often are they actually having you graph f? Maybe visualizing it, but as far as graphing f, 15 identifies, maybe, but that's not really an AP problem. So let's get into our notes section 5.3, because 5.3 says, hey, let's talk about the graphs of all these guys. Let's talk about the graphs of all these guys and how they're all related. This would be a great time to do a graph match of an original function, first derivative, second derivative. But you already did it last year. Now, I have quickly summarized the first derivative, second derivative test and like the solving procedures to get there. Both tests, I tell you to start by checking the domain of f. Because relative extrema, oh, that's right, okay. First derivative test, second derivative test. I'm not talking about increasing, decreasing, and concavity. I'm talking about relative extrema specifically. So we already kind of referred to this, but just a quick, more detailed coverage. First derivative test, I have to know before and after critical points. But I have to make sure those critical points in my head I have distinct from the discontinuities, the domain problems. To consider them all in the chart, but for relative extrema, I'm only looking at the critical numbers of a continuous function. There you go. So I'm disregarding discontinuities. And needing to know the sign of the first derivative before and after the critical numbers. If you guys want, you could, since I don't know if we actually wrote it down anywhere, you can identify f prime equaling 0, disregarding the discontinuities as the stationary points. I don't know if we actually ever wrote it anywhere, we just talked about it. So these are the stationary points, the equal 0, the horizontal tangents, if that helps for you guys to put it somewhere. The second derivative test, you're still checking domain, you're still finding the critical numbers, using the first derivative. Everything's the same until the final analysis. First derivative, sign chart of a first derivative, or I should say checking the behavior of the first derivative. The sign of the first derivative, which indicates the behavior of f. Second derivative, I don't care. Plug it in the second derivative. If there's concavity, I'll know whether it's a max or min. Plug it directly in. No before and after. Just what is the concavity at? So if it helps you guys, remember your first derivative, you need to know before, after of the first derivative. Second derivative, all you need to know is the at. And sometimes the AP forces your hand and all you know is the at, so all you can do is the second derivative test. They love to do that. So quick reminder with relative extrema. This should be pretty close. Wow, it's cold. I'm sorry. Is it just me? I'm freezing. Okay. Making sure the setting's right. Nope, setting's right. Hang in there. What's the next characteristic? Concavity. Looking to the second derivative. But does concavity just tell us about the second derivative? No. What does it tell us about the original? Where? The concavity, yeah. So the sign of the second derivative tells us about the concavity of the first, but what else was on the original function, I should say? What else was on the forever card last year when we talked about concavity? What's f prime doing when f is concave up or when the second derivative is positive? Increasing. Good, because his derivative is positive. And what's f concave down or when the second derivative is negative? Because the derivative's derivative is negative. Sometimes that's helpful. Just a couple of you get confused when doing the second derivative test and you look at the second derivative's pitchfork. That's completely inaccurate. The first derivative pitchfork is all that we use for relative extrema. Just the first derivative's pitchfork. When's the second derivative's pitchfork come into play? Pips. But pips, what's the very first P for? Possible. How do you find actual? And they rarely ever say actual. How do you find inflection points? Change in sign of the second derivative. Or change in behavior of the first derivative. Ooh, that's good. I like that. Especially thinking of graphs. Bless you. Must have change in sign of f double prime, or, which is the exact same thing really, change in behavior of f. Why am I saying that? Because if you're looking at an f prime graph, if the f prime changes from increasing to decreasing or decreasing to increasing, that is a point of inflection of f. Sorry, you had a question. You doing okay? Yes. Oh, at x equals a and b. Sorry. At x equals a and b. The a needs a tail, huh? What I was doing is setting up the pips that I used in the sign chart down here. So then for this example, where is there an actual inflection point? Only at x equals b. Now here's the struggle. What if, for this function, for f, the domain was x cannot equal b? But the sign chart shows that the concavity changes sign. They're so smart. B was a critical, or was a pip, meaning it was a 0 or a DNE of the original function, probably a DNE. And you even were super studious. Maybe that's not the right word. And you did your sign chart. You were being really efficient, and you were saying, I need to check the sign of the second derivative, and you saw it, and you were like, yay, done. What do you still need to check, just like for extrema? Check the continuity, check the domain specifically. Because if the point doesn't exist, well, then there is no inflection point at b, even if there is a change in sign, right? So if this isn't undefined, well, we can't consider him. We still have to do the sign chart and split up there, but that change in sign is only valid at a point that exists in the original. Just a quick heads up. So relative extrema with the first derivative test, second derivative test, concavity, points of inflection. We've just gone through like a week of class in AB. And 3 forever cards? Maybe 4. That was one. Concavity was 1, and then possible and actual inflection points. Yeah, 4 forever cards. Go team. So you guys ready? The directions, in case you can't read them, I'll make it big, are to find all the points of inflection. Possible? No. Actual. Ready? Set. You can collaborate in your groups at some point to make sure you're not going wrong. Go. Go get me the actual inflection points. Psh, use the calculator. Nope. There is no feature that finds inflection points on the calculator. You could look at it and eyeball it. What would be way more efficient if you were allowed to use your calculator? There's a way. You could find a second derivative. That's going to take too long, though. Why not just do it by hand at that point? Find the maxes and mins of the first derivative. You could just take one derivative, graph it, and find the maximums and minimums. Calculator can do that. It can't do points of inflection of the original, but it can do maxes and mins. Remember? F prime, changing behavior. Or you could graph the second derivative and find because that could be all over the place. Your zoom could be off. So then Aryan, you could second derivative, find the zeros. Just watch out for the DNEs. Any vertical asymptotes could be inflection points too. It's not that bad, is it? You guys should have seen the cute ones the A-Bers were getting stuck on today. I know. I'll show you the one I gave them for homework last night. Just one problem. It wasn't that bad. They were just kind of scared. Their goal was just to find the first derivative. Why didn't they like it? Big quotient and product. Bottom minus top. Okay, I'm starting to play. Shh, don't copy me. Do your own work. I've been doing this with A-Bers just to get them to look what they're supposed to be looking. Wouldn't it be nice if something was shared that we could pull out? Would have been nice, but is there anything shared? You take him, he has to distribute to everybody. Take him, he has to distribute to everybody. I'm going to try and do it mental math style. You guys better do it the long way so you can double check that I'm right. That I'm right? Confidence? What? You're welcome. Whoa. I think the x squareds all cancel, right? But with this one. Yeah. It's negative 6x squared minus 4x squared. Oh, yeah, you're right. It doesn't. Negative, no, it doesn't. Negative 8x squared, you're right. Eight x minus 3. Riley, you check.
No, I got -1.
Aww.
I got a +1.
Minus 2.
I got a +1.
Ah, minus 1. You're right. I didn't see the minus.
Well, it's wrong.
What did I just show you? Why you shouldn't do everything mental math. Okay. Good lesson. Why are we going again? When you get the second derivative?
Oh, what? Then why do we
didn't want to do a product rule in the midst of my quotient rule. Did you? It's possible. But there probably would have been something in green that was similar, to be honest. U prime is just 1, yeah? Yay! I have what someone shared. I can pull a 2 out of people. It's all right. Yeah. Yeah. So then that's going to simplify with the bottom just to be x minus 2 cubed, right? Because there's a common one that came all the way out and simplified. Negative 12x squared, anybody? Is there another x squared? There's the negative 16 and then the positive 16x squared. They cancel. And then negative 12x squared? What did I forget?
6x squared plus 8x squared. And then times 2.
Oh, I didn't write the minus 1. That's what happens when you run out of space. There. Is that better? 6x cubed minus 4x cubed is 2x cubed. Negative 16x squared plus 16x squared minus 12. Riley, did you find my mistake?
How come you didn't distribute the negative first?
I don't know.
Because I first distributed the negative, so then there was 6x squared plus 8x. Then times it by 2 is 28x squared. Because like I added them together and then times the whole thing by 2.
I see the whole thing by 2, but what did you put together?
That and the other.
Oh, but only this one should be times 2. Yeah. I didn't pull a 2 out of everybody. You might have, but I didn't. So what we got? 8x plus 32x would be 40x. 40x minus 16. I think that's right. Then we have minus 16. Minus 16 plus 2. Minus 14? Well, don't take it based on my opinion. That's a bad idea. I have 32 plus 8 is 40, right? And 40 minus 16. I think that's right. What's the struggle? What do we still have to do? Find the zeros of the numerator. Wait, who are we going to put in our sign chart still?
2.
The 2 of the denominator, but what is the 2 not allowed to be?
So you can't even do that?
He goes in the sign chart, right? But is he going to be a point of inflection if there's a sign change? No. What did we not get to? Oh, actually the point of the section connecting all the graphs. This homework will be due on Thursday. But if I were you, you felt how long they can get. I might start early. Reflections, thank you, thank you, thank you. Yeah. Yeah, if you turn it in today, you'll get 3/4 credit. Extra, extra, read all about it. Bye, Kathy. Bye, James.